Hello and welcome to lecture number 12. So let me resume from this diagram that I had started last time. So we were talking about smoothness of maps between manifolds, and issue was the following, that the very definition of a smooth map involved the choice of charts, and we wanted to check that if it is smooth with respect to one pair of charts, then it's smooth with respect to any other pair. And this diagram is supposed to illustrate the picture. So the same point P can be contained in two different charts, U phi and U1 phi 1. Similarly, f of P can be contained in two different charts. So let's assume that we are given that f is smooth at P with respect to U phi and V C, and we want to check that f is smooth at P with respect to this this other pair of charts. So, well, the way we defined it, smoothness at P with respect to the first pair would amount to saying that phi inverse this composed map from X, this domain X, to W. So from this to this would be smooth at the corresponding point Q. So this is what we are given, and smoothness with respect to the second pair of charts would amount to saying that this new composed map, which is from X1 to W1, should be smooth at the corresponding point Q1 equal to, there's a small change here, it's phi 1 of P of this. So let's do that. Now I'm supposed to start with this map. And from this I'm supposed to get some information about this map. Well, first of all, let's observe that the smoothness of a map at a point is a purely local issue in the sense that if I can prove that this new map is smooth in some neighborhood of Q1, then that's good enough. I mean, the domain, I don't have to consider this map on the whole domain. Some neighborhood of this, the main point is Q1 should be inside that domain, and if I ensure that this map is smooth in that smaller domain, that's smooth at Q1, that's good enough. So let's proceed. The idea is to bring transition functions into play. So what I do is, let me draw the picture again. U1, and there's my point P. I have F, V1. This is F of P. This point here in the intersection. That's F of P. And F, and then I have this chart maps phi 1, C1. Now let's see where the shaded region goes to. That goes via phi, that goes to something here, and under this it goes to something similarly here as well. So this shaded region we'll go to these two. We have our transition. The point is that these shaded regions here are related by the transition maps. So the transition map here is, so I can start with phi1 inverse. So this is phi1 inverse. I do phi1 inverse and then phi will take me from this. So this transition map here will take me from this red region to this red region. And similarly, here I have another transition map which takes me from, first I do C inverse composed with C1. So C inverse will land me back in the manifold, and then C1 will give me this part. Now what I do is this, once I have this picture, the proof is quite straightforward, because all I do is I'm interested in phi1 composed with F composed with C inverse. So this is a map which is, to begin with, it's defined on this whole open set X1, but I confine my attention to this red shaded region here. So I'll just confine my attention to this part here. And on that part, what I can do is, instead of going via, oh, actually there is a small, so the inverses I put wrong. So actually it is, so I want to first do phi1 inverse and then do C1. Now, as I said, this map is defined on all of X1. But I'm interested only in smoothness at this point, Q1. Q1 is somewhere here in this red shaded region. So I'll confine my attention to just this smaller open set, the red open set. And then on that, instead of just going via phi1 inverse, I'll first go like this. I'll first act by phi1 inverse composed with phi. So this is on, all the action is taking place on this shaded region here. So that shaded region is precisely phi1 of U intersection U1. On this I can write, so first I come here, then, so I need more space, so let me just write it more to the right. So first I do phi composed with phi1 inverse, and then do phi inverse, so that after the first map I'll be in this part here. Now I'll go via phi inverse and then do F. That will land me inside the target manifold. And then I'll apply the map C, which will land me inside this. And then what I should do is I should then so then I'll finally use this transition map to come back here. So C inverse composed with C1. And of course, this is, I've explained it in terms of pictures, but in actually as composition of maps, this phi inverse and phi just give me identity here, and the C inverse and C give me identity here. So all essentially all I've done is started with this 3-term composition. In between this here, I just put phi inverse and phi. Here I put C1 inverse and C. Only thing to keep in mind is that we must keep track of that domain. We have shrunk the domain here. So that's why on this I have this equation, and the manifold condition implies that this is smooth. Now, since we already know that f is smooth with respect to this original pair of charts, this is smooth and this is smooth, again by the transition function. So we have a composition of 3 smooth at the points corresponding to P. For instance, this map, the first map phi composed with phi1 inverse, this map is, anyway, this is smooth everywhere. This is a transition function. The second one is smooth at the point Q. The middle one is smooth at Q. And finally, it's a transition smooth everywhere. So overall, this is smooth. Therefore, this is smooth at Q1, which was the point here. This was Q1. Right. So that shows this explicitly brings out the role of the transition function. So because of the smoothness of transition functions, we don't have to worry about whether some condition holds only with respect to some chart, or the moment you have an atlas, in other words, system of charts where transition functions are smooth, then one can work with, if given a point, one can work with any chart containing that point. Now, there is one important thing that should be mentioned when I define, let's go back a few slides, and when I talk about smoothness of smoothness at P, I have to mention the following. For this composition to make sense, the image of, since I'm doing C of f of something, I want to ensure that f of this u1, actually this is the definition of smooth maps. Yeah, here. So I want to ensure that this map C of f of phi inverse makes sense. In other words, I want containing P, and we say that f is smooth if for any chart containing P and containing f of P. Before I talk about smoothness, I just want to ensure the map is well defined. So I'll say containing such with f of u contained in V, the map, and this. So I'll choose the charts u and v such that f of u contained, we should start with charts u and v such that f of u contained in V. Of course, this can always be done if f is continuous at P. So, but I put this as a condition here rather than adding it, mentioning continuity. This map, this happens. Right. So then as usual, so now that we have a notion of continuous smoothness at a point, as usual we say that f is smooth if it is smooth at all points in its domain. Now let's see some examples. Let's start with the most trivial ones. The most trivial map one can think of is just a constant map. So let's take f of x equals some let n belong to n, and let f of x equal to n for all x in M. So in this case, of course, so as usual, one has to invoke the definition at whenever we want to say. So here, if you want to check smoothness, so here f is smooth everywhere. F is smooth on M. And so the question becomes, which charts do we choose to see this very clearly? We have just proved that it really doesn't matter which charts one works with, but in actual computations, working in a specific pair of charts will make things very clear. But in this case, it doesn't matter. So if I take any chart, so if I take P in M, and f of P is going to be n, irrespective of what P is. So I just take any chart around P, any chart around N, and this composition map will be again a constant map, so it will be smooth. The next trivial map is f from M to M, f of x equals x, the identity map. Again, it doesn't matter which charts we take. So we just, in fact, the easiest thing to do would be, so you take a point P here, f of P is again going to be P. So you can take the same chart for the domain and the image. And when we do this composition, we'll get the identity map on between open sets in Rn, which is of course smooth. Now for something slightly more interesting, let's look at product manifolds. And here there are two natural maps associated to product maps. Let's check that they're smooth. The first one is suppose I have maps between M1 and N1 and F2 and N2. Then I can form this product map M1 cross M2 to N1 cross N2, where this product map is defined in the obvious way, which is I just take F1x, F2y. So this will be again, so if F1, F2 are smooth at P in M1 and Q in M2, F2 respectively. Then F1 cross F2 is smooth at P comma Q. And so to prove this, again it's so here, so one just works with a product chart here, and then it turns out that if you do this, express the map in local coordinates as we have been doing. So by expressing in local coordinates, I just mean considering this C composed with F composed with phi inverse. So if you use product coordinates for that, then one will just get a corresponding map here and a corresponding map in the first coordinate here and a corresponding map in the second coordinate, and one can easily check that this product map is smooth as well. Another thing where I have M1 to N, M to N1, F2 from M to N2, let's say both are smooth at a point P in M. So unlike the previous case, I'm just taking the same manifold as the domain, not two different ones. Then I look at this map f of P, f of x equal to f1x comma f2x x in M. Again, it's f is smooth at P. If both of these f1 and f2, which we have assumed are smooth at P, it will follow that f is smooth at P. And here, so what I can do is, so the fact that f1 is smooth at P will imply that for any chart around P and any chart around f1P, this the composition is smooth. Now to simplify things, I can just use, when I work with f2, I can use the same chart as I did with f1 around the point P. Here of course N2 I'll have to use a different chart, and but on M1, on M, I can use a single chart. But it just it really doesn't matter, it just simplifies notation a bit, that's all. Even if one uses different charts, it doesn't change anything. The other more intrinsic map associated to a product is projections. So I have the first projection, pi 1, M1 cross M2 to M1 pi 2, M1 cross M2 to M2. So pi 1 of xy is just x, pi 1 of xy, pi 2 is y. These are the projection maps, and these maps are smooth. At all points. So again, in fact here, if one takes the product coordinate chart here, and so let's say, so here for example, if I work with pi 1, so let's just quickly see the case of pi 1. So let PQ belong to M1 M1 cross M2, take a product chart. So this we had defined to be of the following form: U cross V, phi cross C. Take a product chart around PQ. Now the pi1 of I'll also need a chart around pi1 of PQ. So this would be this is, in other words, a chart around P. Well, in the product chart, by definition, this U phi is a chart around. So in the product chart, this U and this phi is by definition a chart around P. V and C is a chart around Q. But I don't care about Q. I need a chart around pi1 of PQ, P. So I'll just take the same U phi which I had done earlier. So consider the chart U phi around pi1. Oops, this became messy. Around pi1 of PQ, which is P. If I do this, then so I'll have to basically, so I have here have M1 cross M2 and then M2. This is the project M1 rather, the projection, first projection. And on a portion of this, I have a chart, which was the product chart, phi cross C. And on this, I have, well, this was U cross V. This was just U. Then I have a phi. Right. So if I do phi cross C inverse, compose with pi, compose with phi of x comma y, then I'll end up with, well, after this first map, by definition, I'll get phi inverse x, C inverse y, first projection, and then first projection will give me just the x, the first coordinate here, phi inverse x, which is just x. In other words, this compose the map projection in local special local coordinates like this is again a projection. XY here started with XY here, and I end up with X. And this is true at all XY inside this domain, not just at P comma Q. So it's just the usual projection in between Euclidean spaces. Therefore, this is smooth. So projection maps are smooth, and the other thing is that in the context of products, there's other natural map is a slice map. Slice maps or inclusion maps. M1 cross M2. Again, I start with M1 cross M2. Let B be a fixed point inside, let B belong to M2. Corresponding to this B, I have a map IB of IB from M1 to M1 cross M2. So schematically, So IB of x is x comma b. We'll stop here. In my next lecture, I'll say a few words about this and give some more examples and move on to tangent spaces. Okay, thank you.